Hey everyone, just a quick update on videos here. So this week I'm actually putting up 2 lecture videos, not one. Okay, this will give you the information you need in advance of next week where you do some labs relating to this material. So it's one of those, learn to walk before you run situations. So I want to kind of catch up on the theory this week, give you 2 lectures and, an extra lab, if you like, this week's lab next week. I'll also give you Acid-Base 3 next week. So, next week will be, on Monday, do the final packet of the series. And then Wednesday, you'll have your first lab, and then I'll actually make the other lab due on the Sunday. So the deadlines will be Wednesday for packet 3 next week, Friday for the first of the labs, which will be the week acid titration, and then the buffer one will be due on Sunday. Okay, so I want to kind of get ahead of the material first and then give you the labs. That makes more sense. All right, hopefully that's making sense to you. Any questions? The usual discussion or water cooler chat or office hour. Okay, see you next time. Okay, so we're going to start looking at acid-base equilibria 2. Now remember, we've kind of already done this introductory thing here before, but just to recap, HCl, what's stronger, HCl or vinegar? Well, HCl is a strong acid. It's a mineral acid because it has an inorganic anion. Okay, strong acid, if you like a mineral acid. Okay, why is it strong? Because remember, 100% is OC8. So 100 molecules give you 100 H plus ions if it's monoprotic. Okay, if I have vinegar, and I like to write the anion in brackets, you won't see that in the book, but I do that because it kind of emphasizes that's the acidic proton. That's a weak acid, and it's partial association. Okay, now, if you remember, we did this before. We'll just go over it again just to show you. Okay. So a strong mineral acid dissociates completely. How do you represent that? Oh. The single arrow. Okay, the single arrow means completely dissociated. ICE. Initially 100 moles, 100 molecules, 100%, 0 and 0. Every molecule breaks apart. I make 100 H plus and 100 Cl minus. 2 passengers per car, car stops, 2 people get out, 100 cars stop, 100 guys and 100 girls get out, if that makes sense. Okay, what's left at equilibrium? Just the difference, 0, 100, 100, 100% dissociated. Okay, for weak acids, a little different. I'll do a generic, HA. Weak acids are in equilibrium, so there's always some undissociated acid and dissociation products at equilibrium. Generic A minus. Okay, so ICE, same thing. Initially 100, 0, 0. Let's say for fun it's different this time. Let's say it's 5% dissociated. -5, +5, +5. 95% of the molecules remain intact. 5 H pluses, 5% A minus. So, keep forgetting to shove it up there. There we go. All right. So, moving on. So obviously, because weak acids are in equilibrium with their dissociation products, we can treat them with equilibrium math. Okay, so look at a generic example. So here we have a weak acid, and we say we react with water to make the hydronium ion. We'll show you the simpler version again in a second, and the conjugate base. Okay, so if I write, just straight equilibrium constant, products over reactants, I get that. Okay. Now obviously water is a constant, so a constant times a constant is a constant. So K times the concentration of water, which is a constant, equals a new constant. We call it the acid dissociation constant, which is H3 plus O A minus over HA. So products over reactants. Now remember, H plus, H3O plus are synonymous, and what you'll see in the book is that version right there. Okay, so every weak acid has a Ka, an acid dissociation constant, which is an equilibrium constant, products over reactants. Interestingly, one of the products, of course, is H plus, and we can get into the concentration of that through pH, which we'll show you in a little bit. Okay, so discussion then. Will strong acids have a large or weak Ka? Well, if we think about it, they're 100% dissociated. So products is 100, reactants is 0, so it's effectively infinity. Right? It's no such thing really, of course. It's probably 10 to the 6 or bigger for Ka. Okay, so for HCl, Ka is approximately infinity. Okay, because it's 100% dissociated. It's really, 10 to the 6 or bigger, but we kind of say tends to infinity. Okay, so for weak acids, that's strong. Weak, Ka is in a measurable range, and it's small. It's a little bit of product. It's between 10 to the minus 3 and 10 to the minus 10. So the ratio of products to reactants is between 1,000th and 1/10 billionth. Okay, so 10 to the minus 3, 10 to the minus 10. Oh, do that up. Keep forgetting to do that. There we go. So with that in mind, we can look at some very simple kind of acid dissociation schemes. So if we look here, these are both mineral acids. They have, common, we've seen these before, mineral anions. Okay, so they're both strong. So, HCl and nitric acid are strong. So nitric acid would 100% dissociate. And it's approximately infinite in terms of its Ka. Okay, now down here we have weak acids. How do you know these are weak? You may think, oh, HF, HCl, HF, maybe it's strong. Well, actually it isn't, for reasons we can get into another time. But if you look over here, they all have measurable Kas. If you have a measurable Ka in the range 10 to the minus 3, 10 to the minus 10, something around there, something measurable, it must be in equilibrium. Okay, so they're all weak. And they're all in equilibrium. That's how you'd say it written in the book. I'm going to do my normal thing. That's vinegar, acetic acid, completeness. And finally HCN. All right, so there we have it. 3 weak acids, all showing equilibria with measurable equilibrium constants. Now, interesting question down here. Of these 3 weak acids, which is the strongest of the weak, the king of the nerds, right? Strongest of the weak, and which is the weakest? It's easy to figure out. If you think about it, Ka is a measure of products over reactants. Products are H plus, so the bigger the number, the more H plus. Which of these has the bigger dissociation constant? Well, it's the first one. Okay, so that's the strongest of the weak, and this is the weakest of the weak. Okay, there we go. So the strongest is HF, strongest of the weak, Ka largest, and HCN weakest of the weak, Ka smallest. Okay. I like to do this because, you know, it kind of shows kind of some kind of understanding. Equilibrium lies to the left. This guy at the top here, equilibrium lies to the right. Okay. Moving on. So, as I mentioned, H plus is a product for every weak acid. So, what we can do is wait for my computer to catch up here. Oh, there we go. You probably didn't see that at your end, but having some technical difficulties here, my end with a bit of lag. But we can incorporate pH into a calculation for Ka, or use Ka to work out pH. So we go backwards or forwards. Okay, and we're going to use the ICE method. Yes, corny joke. Vanilla ice, obviously a noted chemical philosopher. Okay, now, if we want to find the pH, how do we do that? Well, remember, nice and easy. Okay, actually, let's read the question obviously first. So, worked example, a sample of 0.1 formic acid, that's the formula, that's what ants actually inject you with if you're interested. So ant venom stings because it has an acid in it. Okay, so 0.1 formic acid has a pH of 2.38, that's an important number. Find Ka. So this is the finding Ka from pH example. Okay, so, and then once we've done that, we can find out the percent of dissociation, which is an interesting number. All right, so plan, do a couple of things. Find the H plus concentration from pH, and then, hey, once we've got the H plus concentration, that's a product, remember, in our ICE table, so we can then go run it backwards if you wish to find Ka. So find H plus first. Now remember, pH minus log of the H plus ion. So if I do a little bit of math there, I'll leave H plus over here just to show you, right? So I move the sign over there, minus pH equals log of H plus, and then 10 to that, that'll cancel, equals H plus. So H plus concentration equals 10 to the minus pH. In our example, 10 to the minus 2.38, which equals 4.2 times 10 to the minus 3 molar. All right, so the concentration of H plus, 4.2 times 10 to the minus 3 molar. Now, that's it. If you remember our classic way of doing an ICE table, and I'll set it up in the classic way. Okay, so acid in equilibrium with its dissociation products. ICE. Okay. 0.1000. We don't know how much it loses, but it's x plus x plus x. It's in a 1 to 1 to 1 ratio. Okay. All right. Before in our previous kind of example a couple of pages ago, that was like 5, right? But we've got to find out what it is. Okay. So 0.10 minus x, I'll keep that together. X and x. I like to kind of emphasize that. That's at equilibrium. Okay, so at equilibrium, K applies, right? So K is products over reactants as our kind of algebra way of doing that. Now, if you think about it, what have we got here? We've got equilibrium values, right? So at equilibrium, concentration of HCHO2 equals 0.10 minus x. Concentration of H plus equals x. Aha! That's our number from before. 4.12 times 10 to the minus 3 molar. And because it's equimolar, 1 to 1, CHO2 x, which is the same number. Okay, so I'll do the algebra work up on the next page, but those are the numbers that we're going to throw in. Okay, so Ka equals products over reactants. That's in that formula. HCHO2. All right. Which equals, go back to the previous page. Both of these were x. X times x is, of course, x squared, divided by reactants at equilibrium 0.10 minus x. Now, here's an interesting thing. This is called the weak acid approximation. Since x is super small, 4.2 times 10 to the minus 3, so 0.004, to two significant figures, 0.10 minus 0.004 is 0.1, okay? So that's always small. So a big number minus a small number is the same big old number. We call that the weak acid approximation. And it's essentially equal to x squared over 0.1. And we can always make that weak acid approximation. We'll meet it formally in a minute. But if you've got a weak acid, Ka is always small, 10 to the minus 3 or smaller. So therefore, a big number minus a small number, same number. Oh, substitute for x on top if we're going to do that. 4.2 times 10 to the minus 3 squared. Finally, at the end of the day, 1.8 times 10 to the minus 4. 1.8 times 10 to the minus 4. Okay, how'd that make sense? Remember, always, we've seen a common theme. You basically do yourself a grid, an ICE table. And it doesn't really matter what kind of equilibrium it is, okay? You can always figure it out from that table. Remembering that the bottom line, I'll show you back again, the bottom line down here is the equilibrium position as defined by K up here. All right, so the percent dissociation, think about it. If I want to figure out how much dissociated, it's what I got over what I started with times 100. So percent dissociation, the H plus at equilibrium over what I started with, HA initial times 100 for a percent, which equals 4.2 times 10 to the minus 3 over 0.1 times 100, 4.2%. So about as strong as vinegar. So ants are essentially injecting you with vinegar. I guess that hurts, right? There we go. So that's the first one. That's, if you like, the forward direction, work out Ka from the pH. You can, of course, run it backwards and work out pH from Ka. So the plan there would be, okay, and here's a problem down here. Again, I'm having a bit of lag here. Bear with me while I just position the paper. There we go. All right, so the plan is, again, do an ICE grid, okay? Work backwards to find H plus from Ka. So we'll rearrange that algebra. Okay, and then once you got H plus, you can solve for pH. All right. So let's go. So the grid, it was 0.2 molar HCN and its Ka was given, okay? So we got HCN in equilibrium with H plus and Cn minus aqueous, of course. All right. ICE 0.200, do the usual procedure. It's monoprotic, right? So it's 1 plus 1 plus 1, don't know how much, that's x. 0.2 minus x. And again, that's weak acid approximation, 0.2, x, and x. All right. Ka then equals products. This one times this one, which is x squared, over 0.2 minus x, which again is approximately equal to x squared over 0.2. That's the weak acid approximation again. Okay, because we assume that x is super small compared to 0.2. All right. Therefore, flip back. Ka was 4.9 times 10 to the minus 10, x squared over 0.2. Therefore, x equals h plus, which is what we're after, that's our focus, which equals this times this square rooted. (9.9 times 10 to the minus 6). Therefore, pH equals minus log of h plus minus log of 9.9 times 10 to the minus 6, which equals 5.0. Okay. Oh, again, off the bottom of the page. Excuse that. Okay. So I just ran the algebra. Ka x squared, just rearranged to find x, which is h plus, minus log of h plus. Okay, and there's a formalization of the weak acid approximation. Okay, now it says group work. Okay, we got a couple of old exam questions on this. Okay, and what I'm going to do, which is kind of neat, I'm actually going to assign this for a little bit of extra credit homework. Okay, so what I'm going to do, this is the interesting thing. Okay, work out problems take a picture of all your work on your page and then send as email attachment. I'll make it worth 5 points. Actually, make it worth 6, 3 each, because there's 3 times 2 points. There's 2 questions, right? Okay. So if we look at the back of the book, the back of the packet, we'll do weak bases in the next thrilling installment, right? Okay. So that's the next packet. Sorry, that's the next video. Okay. In the back of the packet here, we have a couple of old exam questions, all right, and both of these are going to be worth 3 points of extra credit. Okay, what's the pH? So I've got, it's my classic favorite question, the same concentration each time, but I've got 3 different acids. I've got a monoprotic, diprotic, both are strong, then a base, okay, and then a weak acid, and you do the whole grid thing. Okay, so you get 3 different pHs for 3 different solutions, all of the same concentration. I like that question a lot. So work on that. Send it me. I'll put in the, you probably read it, in the discussion, I'll write a deadline for that. Probably give you a week, all right? And then the next one, weak acid, it's a more formal weak acid. We're actually going to work out a bunch of things. Got a weak acid, and you're working backwards, so check the previous question when we work out the percent of dissociation. Work backwards to find H plus, HA, and Ka for this. That's at equilibrium. Okay, the equilibrium concentrations of H plus and HA and Ka for that solution. All right. All right. Of course, you can use the weak acid approximation, so big hint. Yeah, it's the same number, isn't it? Okay. All right. So we'll do the weak base one after we finish the weak base work. All right. So I'll stop there. Any questions? Please feel free to comment in the discussion area, and we'll see you on the next one. Okay, so we're back to talk about weak bases. Okay, now weak bases, similar kind of ICE grid situation, but remember this time hydroxide ions will be the product. Okay, so when we have a weak base, we're going to find through an equilibrium setting up the OH minus ion concentration. So when we work through the pH, we'll have to go through POH, which is the minus log of this thing, and then do a little kind of conversion at the end from from POH to pH. Okay, so the classic example is of course ammonia. Okay, so ammonia is the weak base kind of poster child, so to speak. Okay, so we'll do a similar kind of work through like we did with the acids. We'll determine an equilibrium constant expression. Okay, so we have ammonia, which is a base, picks up a proton from water to make ammonium and hydroxide in solution. Okay, so we have, if I do a simple K expression, K equals products over reactants. Okay. Same deal as before. We can derive a new constant from combining a couple of constants here. So we'll just do that real quick. So K, oh, I've moved it out a shot, but let's bring it back. There we go. K times the constant, which is the concentration of water, equals a new constant, B for base, Kb, okay, which equals NH4 plus OH minus over NH3. There we go. Okay, if I'm more generic here, Kb for a generic equals conjugate acid times OH minus over B for base. We're using a more generic kind of form. Okay, so I always like to remember the ammonia example. I'm kind of a solid example kind of person. If you like a more generic kind of one, that's good too. Okay, so as we saw before, mineral acids were strong, mineral bases are also strong. Okay, so mineral bases or strong bases simply have OH as a straight passenger, right? So OH is in this salt essentially, which is a strong electrolyte pair. It completely dissociates. So whenever we see a kind of a metal with something, it's going to fall apart to make 100% ions in solution. So it's strong, it completely dissociates. Okay, so here we have another situation. This is also strong. You know, we can use KOH and NaOH interchangeably in lab. They do exactly the same thing. They give you a nice amount of hydroxide ions in solution. For every one KOH, I get one OH. For every one NaOH, I get one OH. Oh, typo. KB. KB, all products, now reactants at equilibrium. Equilibrium, speech marks, right? It's not really an equilibrium, it's a complete reaction. Okay, so then we have these, okay? We have, each of these has a recorded KB, so they're all weak. These are all weak, okay? Because they have KB values. A bit like if you have a Ka, they're all weak acids. Well, these are all weak bases. And we can do our, it's not, remember, a direct association for weak bases. It's actually reacting with water to make OH. So the weak base picks up a proton. Oh, to make hydroxide. That's a 4. Okay, we saw that one on the previous page. Okay. Similarly, maybe pause here and give those a go if you wish, but I'll just go straight with it. Pick up a proton. And finally, this is the one from your lab you're hopefully working on, right? Okay, so there we are. the bases pick up a proton from water to leave OH behind. Okay. Now, just like before, who's the king of the nerds, right? So who's the strongest of the weak? Well, remember, it's all about value of KB. The largest number here is actually the bottom number. Okay, 10 to the minus 4 is the largest value there. CO3 2 minus. This is why lots of natural sources of water are slightly alkaline. You go to the supermarket, you say, oh, alkaline water. It just has naturally dissolved calcium carbonate or chalk in it. Okay, so no biggie. All right, the weakest weak bases, look at the numbers, 10 to the minus 7, hydrogen sulfide ion. Fair enough. Okay. Recall products over reactants. A small number means less products, a large number means more products. Okay. Next page, we'll get on to some questions. So in a similar kind of way we did before, there are two kinds of questions, if you like, the forward question and the reverse question, just like with the acids. But here, remember, we have OH as a product, okay? So when we do the minus log of that, we're going to get POH, and then pH plus POH equals 14, if you remember that relationship, okay? So we get this one, minus it from 14 to get pH, because we always quote pH rather than POH when we, when we do a question, right? So let's look at this. So find the OH minus concentration and pH for a 0.15 ammonia. Kb is known. Okay. So the plan, go to the ICE grid, solve for OH minus ion concentration, which is going to be X when we get to it. Okay. And hey, if we've got the OH minus concentration, well, you can find POH. And then, hey, use the relationship here to find pH. Okay, so quite similar to the previous question, but the little twist on the end is always converting POH to pH. All right, so the execution. I'm kind of trying to be mindful to keep pulling this up so it doesn't go off the bottom of the page. I did see that. Okay, so NH3, H2O, NH4 plus OH minus. Okay. ICE. Did say at the top 0.15 moles per liter. The concentration of water is meaningless. It is a reactant, so we got to write it, but its concentration is meaningless for the math, if you remember. Okay, it's a constant. And then we have 0, 0. We don't know how much we lose, but there's 1 to 1 to 1 to 1. We lose X, we gain X. So 0, of course. Okay, then at equilibrium, what have we got? 0.15 minus X, X, and X. I know what you're saying. You're saying, when can I get out of the house? No, you're saying, can I do the same kind of approximation here? We did the weak acid approximation. Can we do a weak base approximation? Yep, we can. We can do the weak base approximation because KBs are a similar magnitude to KAs. Therefore, KB equals products, X times X, X squared over reactants, 0.15 minus X, small, X squared, approximately equal to X squared over 0.15. Therefore, I'll come down here. Therefore, X is the OH minus ion concentration, which equals X, which equals KB. Let's put the number on it. Okay. So let me try and neaten this up a bit. KB was 1.8 times 10 to the minus 5. All right, that's KB. So x equals kb, 1.8 times 10 to the minus 5 times 0.15, like the very similar example, square root, which equals 1.6 times 10 to the minus 3. Running out of space a little bit, okay. Therefore, POH equals minus log 1.6 times 10 to the minus 3, which equals 2.8. Therefore, pH equals 14 minus 2.8, which equals 11.2. Makes sense, right? The pH of a base is 11.2. Shocker, right? Okay. Group task. It's the reverse problem. Okay, it's the reverse problem. I want you to try that. Okay, normally if we did this in class, I'll have you work on it in little groups, and then we go through it. The answer 0.0056 molar. Hopefully you get that. If you don't get that, ask a question in the comments area. KB, it's on the previous page, but KB for ammonia, 1.8 times 10 to the minus 5, you can use that. Okay, so that's the reverse problem. Feel free to confer with each other, ask me questions if you wish. Okay. Now, in the same way there's a relationship between KW and then PKW, H plus, OH minus, pH, POH, Ka and Kb also come into that relationship. Okay, and I want to show you the relationship between Ka and Kb with just a simple little bit of algebra, right? So I've taken the classic ammonia example. Here's ammonium acting as an acid, okay? Here's ammonia, which we just saw, acting as a base, okay? So that's like the reverse reaction from above, right? So for that reaction, Ka equals products, H plus NH3 over H4 plus. Fair enough. For the reverse reaction, it's this one, Ka in the reverse reaction, Kb in the forward direction, acts as a base in the forward, acid in the reverse. Products, NH4 plus, OH minus, NH3, okay, H2O. All right, now, if you remember, when we add reactions, we multiply K's, all right? So let's do that. So we're gonna add, and feel free to pause, give this a shot yourself. For speed, I won't write the state symbols, but you can do that. All right. What cancels? Well, NH4, NH3, H2O, and H plus, OH minus. Oh, interesting. Okay, so if you remember, KW equals H plus times OH minus, okay, which equals, add equations, multiply these guys, which equals Ka, Kb. If you actually multiplied these two together, you would find things cancelled, okay? So if you want to bring that up and multiply it through, you'll get what would be left would be the same, okay? All right. So equilibrium math can be applied. Okay. Very, very simple idea. Let's write it down. Another equation to remember. Okay. Kw equals 1 times 10 to the minus 14, which equals H plus OH minus. That's what we've seen before. And it also equals Ka times Kb. If you like, it's the equilibrium constant for the forward reaction times the equilibrium from the constant from the reverse reaction equals Kw. Okay, because remember, this all happens in aqueous solution. This is all in the background, right? Okay, so, you know, some more reactions to remember. If I take the minus log of both sides, I get that. Okay, in much the same way as pH plus POH equals pKw, pKa plus pKb equals pKw, right? Where pKw is, of course, 14. Okay, so very similar. So a quick question. What is Ka for NH3? Well, Kb, as we saw in the previous question, 1.8 times 10 minus 5. Now if you think about it, Kw equals Ka Kb, therefore Ka equals Kw over Kb, 10 to the minus 14, 1.8 times 10 minus 5, one off the bottom, 5.6 times 10 to the minus 10. Okay. All right. Now, there is an old exam question. And yes, extra credit. Okay. So, just like the last one, we'll make this one also worth some extra credit. Okay, I'll talk you through it a little bit though. Okay. So here are the previous 2 extra credits. Hopefully you're working on these. I'm going to send me those pictures. Okay. So, talk you through it. Codeine, weak organic base. Codeine has a pH of this, right? So the key word here is base, right? So work out Kb. You're going to do a grid. Okay. Calculate pKa. So once you've got Kb, you can turn it into Ka, just like we did, and then turn it into pKa. So there's kind of a, So there's a friendly roadmap, okay? So you've got Kb from the first part. Similar math to we just did at the previous page to find Ka, take the minus log in base 10. And everyone's happy, all right. That'd be plus 3 extra credit. Okay, so, you know, maybe you want to send it with your acid work. I'm recording this all on the same day, so let's try and make it a week from now. So the 7th. Okay, April 7th. Okay, so get this done by April 7th. Okay, some nice pictures to finish off. This is all in the appendix. We see full dissociation, partial dissociation, basically pictures from your textbook. That classic strength chart we used before. Another copy in here as well. So if you use that one on the last packet, you can use it here too. And some examples of common acids and bases. Okay, and you can just go through on some blank paper. Okay, that's the last one. All right, so we'll stop there. Again, any questions, discussion? See you next time.